Good morning. Welcome to the course of Analysis of Structures 3. This is included as a third paper of analysis in the 2012 scheme of B.Tech in Civil Engineering in the Cochin University of Science and Technology. Well, analysis essentially means determination of internal forces in a structure. And we know that a structure is a load carrying member. In this particular subject, 2 or 3 methods of analysis are being discussed. As a prerequisite to this course, we require analysis of determinate structures, strength of materials, some portion of strength of materials, analysis of indeterminate structures, a few methods of them to some extent. We know how to find out the deflection and slopes in beams. We know how to find out the axial forces in trusses. These are being discussed in the first year course of engineering mechanics, second year course of strength of materials, and second year course itself of analysis of structures 1, that is analysis of determinate structures. In the previous 2 analysis of structures, that is 1 and 2, several methods have been discussed to analyze statically determinate as well as statically indeterminate structures. Now here, in this method, what is essentially included is matrix methods of analysis of structures. Irrespective of determinate or indeterminate, matrix methods are included in this particular subject. Once you undergo this course, you will be able to appreciate computer methods of analysis of structures. What are the methods used in a computer to analyze structures? Let it be pin jointed structure or rigid jointed structure. Let it be a plane structure or a space structure. A systematic method of analysis of structures is being covered in this subject. So a student who undergoes this course will be able to understand matrix methods of structural analysis of determinate as well as indeterminate structures and appreciate the computer application of analysis of structures. That is essentially the outcome of this particular course. And also, towards the end of this course, towards the last module of this course, the finite element method is also included. A smooth transition from matrix methods of analysis to the FEM, the so-called finite element method of analysis, is also possible. And as we are aware, the finite element method of analysis is not only used for discrete structures but for continuum structures also. So at the end of this course, a candidate or a student will be able to appreciate the FEM also to some extent. The introduction part of FEM is also included towards the end of this subject. So that is what I have to say regarding the introduction to the subject. Now, we will go ahead in this particular subject in the following sequence as it is given over there. We will see from the scratch for completeness of this subject, what is a structure, what is analysis of a structure, what are the basic assumptions made in the analysis of a structure. We will see what is determinacy and what is indeterminacy of a structure. We will discuss about, on the basis of the previous section, we will discuss about what are force methods of analysis and what are displacement methods of analysis. Then the method of consistent deformation, which is the fundamental to one of the matrix methods of analysis, is going to be discussed in detail. And following that, the flexibility method of analysis will be discussed. Further, in the displacement method of analysis, we are going to discuss about the slope deflection method of analysis, which is a precursor to the stiffness matrix method of analysis. And then we will discuss about the direct stiffness method of analysis. And further, towards the end of this course, we will discuss about the finite element method, introduction to that. In fact, the last section itself is a full subject. We require a full course for that, but as part of this syllabus anyway, that is included as a module towards the end of this subject. So we will appreciate that too towards the end of this subject. So as part of this section, we are going to discuss the first two sections. That is, what is the structure, what is meant by analysis of the structure, what are the basic assumptions, which are actually covered in analysis 1, analysis 2 also. But for completeness, I am going to repeat the same thing in a nutshell quickly. And further, we discuss about determinacy and indeterminacy of structures. Well, structure. We know that a structure is a member or a component, we can call like that, which carries some load. To a layman, a structure can be a building. It can be a bridge as a whole. It can be an electrical tower as a whole. So anything which is seen to seem like, say, a tall thing can be a structure to a layman. But to a civil engineer, a huge structure like a building or a bridge is divided into components. For example, a beam in a building or a bridge can be a structure which carries certain load and transfers that load into another structure or finally to the foundation or to the soil finally. There are elements in a building or a bridge which are non-load carrying members which cannot be called as structures also. For example, a door or a window, a door frame or a window frame. They are non-load carrying members. They are not going to come under the category of structures. So any part of a building, any part of a big structure which is designed to carry load and which is designed to transfer the loads to other structures or finally to the soil can be called as structures. Essentially, that is that. Structural members, as it is given there, they can be idealized as discrete structures or continuum structures. For example, a beam or a column. Column is a vertical member. A beam is a horizontal member which carry load. They can be idealized for analysis as a discrete structure. On the other hand, a slab, say a roof slab, say a concrete wall or a retaining wall can be idealized as a continuum structure. In this particular subject, we confine ourselves to the analysis of discrete structures. As given here, a beam, a column, a rigid jointed frame consisting of many such beam and column elements, a pin jointed frame consisting of axially loaded members are examples of idealized discrete structures. A beam is generally a structural member carrying transverse loads. A beam would be lying horizontal, maybe generally it would be horizontal, and the loads are going to be vertical. That is an example of a beam. A beam can also be inclined. There are special kinds of beams like that, but generally a beam is a horizontal member which carries vertical loads. The inclined loads also can come, but generally the loads are going to be vertical. As I discussed, a slab, plate, shell or 3D beam, a retaining wall or other kinds of masonry or concrete walls can be coming under the category of a continuum structure. Analysis, as we discussed in the beginning of this class, it is essentially determination of internal forces like axial forces, shear forces, bending moments, etc., and deflection and slope in a structure. To design a structure, finally, the whole aim of analysis is to design a structure. Design means making a decision making. So there we need to make a decision upon the size of a structure, the shape of a structure, the material of construction, and the methods of construction. So in that, to decide upon the size of a structure, the shape of a structure, and the material to be made use of for construction, we are required to analyze the structure for, as it is given here, axial forces. Sometimes axial forces are forces acting along the longitudinal centroidal axis of the structure. Bending moments are moments which are trying to bend a structure with respect to the, say, axis perpendicular to the longitudinal axis. Shear force are forces trying to shear or break a structure along a cross section or otherwise. Deflection, the internal forces are important to a structure, and when you design for serviceability criteria, the deflection has to be limited to certain extent, the slope has to be limited to certain extent. So design codes are there which give limitation to deflection and slope also. For example, if you have a structure which is giving a deflection of say 1.5 meter in a building, in a room of height say 3 meters, is going to be affecting the functionality of that building. So deflection, excessive deflection is going to be out of question for a structure. Now, as given here, this is an example, an idealized example of a truss member. We have an axially loaded member which is drawn like a straight line. The straight line over there represents the centroidal longitudinal axis of a structure, and T and T, those two arrow marks shown on both sides of that line segment, they represent axial forces, and T stands for a tensile force. Generally, capital letters in English represent forces. In general, you can see the capital letter LAE, which is written below the beam. They represent length of the beam. A stands for the area cross section of the beam, and E stands for the Young's modulus of the beam. They are the geometric and material properties of the structure. You can see here a beam in general. For more clarity, let me go for so this represents the longitudinal centroidal axis of a beam which has material properties Young's modulus, geometric properties area cross section as A, and length as capital L. What is shown here like this is a possible deflected shape of the structure, and this is the rotation or slope of this end of the structure of the beam. This much is the deflection at this end of the beam. The slope of a structure at a point is calculated as the angle between the initial tangent drawn to the structure, drawn to the centroidal longitudinal axis of the beam, and the final tangent drawn to the elastic line, which is the deflected shape of the structure. So here, as you can see over here, theta A is clockwise from the initial tangent to final tangent. It is clockwise. It goes like that, this way. And deflection is generally because transverse loads are perpendicular to the longitudinal axis and they are downwards. Deflection is going to be downwards, measured downwards as positive. Here at point B or the end B of the beam, delta B is the deflection and theta B is the rotation. Fa is the shear force at this end, Ma is the bending moment at that edge. Similarly here, Fb represents the shear force at this end and Mb represents the bending moment at that edge. So these are the notations which we generally use for pin jointed on top and rigid jointed below structures. And we also assume that the structure is linearly elastic, isotropic, and we go for only the first order analysis. That means the stress strain curve of a structure is linear. Stress follows strain, or the relation between stress and strain is going to be linear. That is the first assumption. Elastic. The deformation is going to be within elastic limit, beyond which the material is going to be inelastic, or it cannot come back to its original size and shape if we go beyond the elastic limit. So we assume that when you remove the load at any point of time, the material can come back to its original size and shape. That is why elastic. Isotropic. The material properties are going to be having a point of symmetry. Properties like Young's modulus, Poisson's ratio, other moduli, they are going to be same in all directions. And we go for only first order analysis, or we go for only, say, small deflections. We do not go for large deflections. Even if a structure is elastic, it can depict, say, large deformation. So that is not going to be covered in this section. So we go for only small deflection or small deflection analysis.